Hello, my name is Ben Lubin from Boston University, and this is joint work with Sven Seuken, Manuel Beyeler, and Gianluca Brero. In this work, we study combinatorial auctions. In particular, we focus on large combinatorial auctions with many items in a domain where the bidders can have general preferences involving substitutes and complements. A typical example is a spectrum auction like the Canadian 700 MHz spectrum auction, which had 10 bidders and 98 different licenses. These gave rise to 2 to the 98 bundles of licenses. We know from Nissan and Segal that if we wanted to guarantee full efficiency, this would require an amount of communication that's exponential in the number of items. Thus, we need to design a mechanism with smart preference solicitation. The current state-of-the-art mechanism for such domains is the combinatorial clock auction, or CCA, which has been used to generate more than $20 billion in revenue. However, lab experiments have shown that due to imperfections in the bidder behavior, the efficiency achieved can be only between 89 and 96%. And note that even a 1 to 2% efficiency loss in a large auction like a spectrum auction can correspond to $100 million of welfare losses. This motivates the design of new auctions, such as the one we consider in this paper. This paper builds upon our own prior work, where we designed a machine learning-powered iterative combinatorial auction, which we call MLCA. To briefly summarize MLCA, it uses a machine learning algorithm instead of prices to steer the auction round over round. Graphically, you can think about it like this. There is an auction mechanism which in every round sends a query to the bidder asking the bidder for his value report for a specific bundle. Once the value report has been received, the machine combines it with any earlier reports and generalizes in order to predict the bidder's preferences over the full bundle space. The mechanism then proceeds iteratively to ask multiple additional queries until a certain cap has been reached, and then it computes final allocations and payments. While we have shown that this performs very well, there is one main limitation, namely it requires exact value reports for every query. But this can be very costly in practice because bidders may need to solve a complex profit optimization problem. Or in some domains, it may even be impossible because of inherent uncertainty regarding the value of a bundle. And therefore, in this paper, we design a new mechanism, which we call iMLCA, which is MLCA with interval bidding. This allows the bidders to report a lower bound and an upper bound on an interval that contains their true value for a bundle of items. Next, I will briefly compare the auction phases of MLCA and iMLCA. MLCA has 3 auction phases. In the first phase, initialization, we query a set of random bundles to generate some input for the machine learning algorithm. Next, in the iterative machine learning phase, we then use a very sophisticated machine learning-powered query module to generate a vector of new queries in every round. Importantly, this vector of queries, with 1 query for every bidder, constitutes an allocation. Thus, we know the elicited bundles will be feasible. In MLCA, there isn't excess demand, as there is in the traditional ascending price auction, and the center ensures that bundles will fit well together. In prior work, we have shown how the mechanism can use several popular forms of ML, including support vector regression, deep neural networks, or even Fourier-based methods. Finally, in the outcome determination phase, we compute the final allocation and the payments based only on the reported bundle value pairs, so there's no machine learning involved in this last step. In iMLCA, we now modify the second phase such that bidders are both queried additional bundles based on ML and forced to tighten their bounds according to an activity rule. Next, we add a new convergence phase where we further refine the bound according to additional activity rule such that we obtain convergence guarantees. I will now describe these 2 steps in more detail. The query module with interval bidding extends our earlier query module in MLCA. For this, consider the value of the kth bundle that bidder I has reported, BIK. The idea is that we can exploit the epsilon insensitive loss function that is used by standard support vector regression algorithm. This loss function provides that there is no penalty for a prediction within an epsilon interval above and below the supplied label. In iMLCA, we can exploit this by doing the following trick. Given an interval report VIK lower bar, VIK upper bar, we can create an artificial report VIK, which is set at the midpoint between the reports. And then we can supply a label-specific error term epsilon ik, which is simply the upper bound minus the lower bound divided by 2. And observe that by doing this, you obtain no penalty in the training for any prediction within precisely the range of the stated interval, and standard linear loss is outside it. This implies that we can simply train the support vector regression algorithm on this new artificially generated midpoint report and the corresponding error terms, and obtain a correct semantics for our elicitation process. Next, we need to force bidders to refine their bounds in every round of the auction. To do this, we employ an activity rule based on the price-based refinement of earlier work. The rule will force bidders to tighten their bounds on specific bundles, and to do this, it first computes a provisional allocation. We find the provisional allocation by computing a provisional valuation function for every bidder, which is simply a convex combination of their lower bound and upper bound. And given this, we then compute the welfare maximizing allocation corresponding to these provisional valuations. Given the provisional valuation and the provisional allocation, we then compute approximate linear clearing prices, and this is done by solving a sequence of linear programs and quadratic programs to minimize the clearing error. There is some complexity in selecting approximate clearing prices, and I refer you to the paper for details. Finally, we apply the so-called modified revealed preference activity rule, MRPAR. Informally, this requires every bidder to reveal one bundle that is preferred to all other bundles. Graphically, this can be illustrated as follows. Suppose the bidder is considering 3 bundles that she has already reported, the current provisional allocation bundle on the left and 2 others. Suppose the dots are the true utilities at the current prices, and the horizontal lines indicate the current lower and upper bounds on utility. How does the bidder show to which bundle is most preferred such that she can satisfy the rule? She can pick a level and then increase the lower bound on one of the bundles to this level and decrease the upper bound on all the other bundles such that the intervals are not overlapping anymore. This makes clear which bundle is most preferred at the current approximate linear clearing prices. Note that after phase 2, we may still not have clearing because linear prices may not be powerful enough to clear in our combinatorial setting. That is, MRPAR is only delta converging for delta approximate linear clearing prices. We therefore imply a third phase with a stricter bound refinement such that we obtain a convergence guarantee. To do this, we employ a second activity rule, which requires the bidders to tighten their bounds on carefully chosen set of bundles, such that their reported interval size is smaller than a specified epsilon. This epsilon is then reduced round over round. By doing this sufficiently often, we can show that the implemented allocation will converge. Because it is technical, I will defer to the paper details on how the specific subset of bundles necessary for this condition is selected. I want to now briefly summarize the properties of iMLCA. First, it is a very practical mechanism because the auctioneer can tune many parameters, such as the maximum number of queries or the maximum number of rounds that the mechanism will use. Second, it satisfies individual rationality as well as no deficit. We need to be most careful in describing the incentive properties. While it is not strategy-proof, we can use VCG or course-selecting payment rules at the end of the auction to induce good incentives in practice. I also want to emphasize again that the allocation and the payments are only computed based on the elicited bids. ML is not employed in computing the final outcome, so the bidder does not have to care about the details of the machine learning algorithm, but only about the set of bids elicited at the end of the auction. Moreover, if the bidder has some information that she deems valuable for the auctioneer to have in order to determine the efficient allocation, she can push this information to the auctioneer in the form of push bids without changing the properties of the auction, and this will only increase social welfare. And finally, we explicitly query all of the marginal economies, that is, where one bidder is excluded. Performing such queries will reduce the manipulability of VCG or course-selecting payments that make heavy use of such marginal economy information. Of course, I also want to mention that iMLCA does have a larger strategy space than MLCA because the bidder can now manipulate both her lower and upper bounds, and this opens new questions regarding whether there are some manipulations that will prove effective for the bidders that did not previously exist. I want to now show you some experiments we did to compare the efficiency of the CCA, MLCA, and iMLCA. For this purpose, we'll use the Spectrum Auction Test Suite by Weiss et al. To create hundreds of random spectrum auctions instances on which we can compare the different mechanisms. I want to focus on the setup of iMLCA and how we simulate the bidders. The interval reports are created using a truncated normal distribution. We sample two error measures, Z1 and Z2, from the normal distribution, and then the upper report is simply the true value plus Z1, and the lower report is simply the true value minus Z1 truncated at 0. As an example, this could lead to an interval report that is, say, between 1,000 and 2,000. Here, VIK will lie somewhere in the middle between 1,000 and 2,000, and note that because Z1 and Z2 are drawn independently, our intervals are not centered around the true value. And finally, for all mechanisms, we will simulate straightforward truthful bidding. The first domain for which I want to show you the results is the GSVM domain, which has 7 bidders and 18 items. And here, all of the 3 mechanisms we tested perform very well, with all getting essentially 100% efficiency. Note that iMLCA has to operate with much less information because it only has an upper and lower bound instead of the true value from every bidder's report. Here, we are working with only 100 bids per bidder while still achieving this high efficiency. The explanation for this is that in GSVM, only two-way interactions between the items matter, which implies that the machine learning algorithm we use for MLCA and iMLCA can actually capture this domain perfectly. The second domain I want to show you is called LSVM. Here we are dealing with a more complex value function where the values for a bundle depend on the number of items and also the location of those items in a grid, ultimately producing a sigmoid-shaped value function. Here, all of the mechanisms achieve slightly lower efficiency, with CCA being the best at 99.9%, and MLCA and iMLCA at 99.6%. This is now achieved with a larger query cap of 500. Note that iMLCA again achieves the same performance as MLCA with less information. The explanation for why the CCA is achieving such good performance here is that in this domain, even though we have a more complex value function, the bidders are essentially only interested in a small number of bundles, such that the CCA in the supplementary round can actually elicit almost the full value function for most of the bidders with a query cap set at 500. The final domain that I'd like to show is the MRVM domain, which is modeled on the Canadian 700 megahertz auction that I mentioned earlier, which has 98 items and thus has 2 to the 98 bundles. Here, all of the mechanisms achieve significantly less than 100% efficiency. We are again using a query cap of 500, and this time MLCA is performing best with a 96.4% efficiency. iMLCA achieves 96.1% efficiency, and the CCA around 94.2% efficiency. All of these differences are statistically significant. Here we see that in a realistic domain, the ML enables interval queries to achieve a very high efficiency, even compared to the state-of-the-art benchmark. Next, you may wonder if the advertised benefits of iMLCA actually show up for the bidders, or after many rounds of refinements, do the bidders have to refine their bounds all the way until they actually end up reporting an exact value report anyway? I want to show you that this is not the case. For this, we measure the reported interval size before and after the auction has taken place. We capture this interval size as VIK upper bar minus VIK lower bar divided by VIK upper bar, and then take the average over all of the given interval reports. To make this clear, let's return to our earlier example. If the bidder makes a report of 1,000, 2,000, the measured uncertainty here is 50%. In our auction, we had an initial interval size of 55%, and by the end of the auction, this was only reduced to between 41 and 48%. This shows that the intervals were still relatively large even at the end of the auction. With this, I want to conclude. I have shown you the design of iMLCA. And in particular, we have seen how it exploits the structure of SVRs to handle interval queries. We have combined a machine learning-powered query module with price-based refinement to drive elicitation in the same auction phase. We've also introduced a novel convergence phase that handles the fact that linear prices may only be approximately clearing in our settings. There are a number of interesting future directions for work, including interleaving phases 2 and 3, using more complex prices to speed up refinements, and extending iMLCA to use other machine learning techniques. Thank you very much.